Thank you, and thank the organizers for getting me here. And today I would like to talk about my joint work with Anand Shankar on exceptional splittings of abelian surfaces with real multiplication. So let me start it from state the main result. So throughout this talk, F is a real quadratic field. A is an abelian surface over a number field. With real multiplication by F, namely that the endomorphism ring tensor Q contains F. So I would like to put a very naive-looking question. So how often does A have simple? By simple, I just means simple as an abelian variety, are non-simple reduction mod V. So throughout talk, V will always denote a finite place of K. So there's a conjecture by Muti and Patenka. They actually talked about general abelian varieties over a number field, not necessarily an abelian surface. So they conjectured that A has geometric simple. So by geometric simple, I mean that you pass through an algebraic closure, then it is simple. Geometric simple reduction for a density 1 set of primes of K. Here we may need to pass through a finite extension of K. So after suitable field extension, finite field extension. If and only if the endomorphism ring of A over an algebraic closure of K is commutative. So let me just make a quick remark. Is like if the endomorphism ring is not commutative, means it's some division algebra, and then you just pick a place such that the division algebra splits. So that gives you a GLN, which will split the abelian variety. So this part is easy. And the conjecture is proved by Zewiner in 2014 under Manford-Tate. So conjecture holds under the Manford-Tate conjecture. So in this case, when we talk about abelian surface, the Manford-Tate conjecture is already known. So that's why in this case we know that there's a density 1 set of primes such that the abelian surface has simple reduction. Let me just remark that actually in Zewiner's proof, he also make explicit what is the suitable field extension. Is the field extension such that the GL, which is the algebraic L-adic monodromy group, which is the Zariski closure of the Galois group GK X on endomorphism of Tate module of A of the image. So when this one is connected, so this one is connected, that is the field, that's the finite extension. Okay, so the question is like, what about the density 0 set when, so what about the density 0 set when A over, so I use FV to denote the residual field of place V, when A over FBR is not simple. So the answer is actually our theorem. Whether that, so AFV bar is not simple for infinitely many primes. So this density 0 set is actually infinite. So let me make a couple of remarks. So the first remark is, so when I discuss the proof, and actually the key part is we'll assume, so the endomorphism ring tensor Q is actually F. Because if you have a larger endomorphism ring, which means it's either A is not simple, or you have CM abelian surface, or you have a quaternion algebra multiplication. In all cases, you can see. In that case, actually, the density 0 set is just a density 0 over whatever field you have, but it is a positive density over Q. That's why you can use Chebyshev density theorem to get the conclusion. OK, so the second remark is, so since this is a set density 0 but infinitely many, like how large it is, do we have some asymptotic estimate? So if we assume that endomorphism ring A is equals to Z, this is still an abelian surface. So it is in the paper by Archer and Horn in 2017, and with a computation by Sutherland. They did some numerical computation, and which gives the conjecture that such set of primes, so that they only did the case when A is over Q. So the number of primes L less than a capital X, such that AFL not simple, is approximately some constant times X over, so X to the half over log X. So which means like for at least some cases, the Chebyshev density theorem is never going to win for you for this theorem. OK, so and the similar estimate holds when you have real multiplication. This you can do by Settle-Tate and Land-Charter type of heuristic to get a similar asymptotic guess. OK. So third remark I would like to make is I would like to make.
I'll ask you this every single time.
Yes.
To a lower bound.
Yeah, I told you last time we can get log X. I think last time I mentioned to you that we should be able to get a log X. But this part is not in the paper, so don't trust my words for that. Yeah. OK, now I'll erase this part. Yeah, so but like I don't expect our method will give you any positive power. OK, so the third remark I would like to mention is like what kind of similar results that when you have a set of prime of similar asymptotic, and we also have infinity many. So the first result I definitely would like to mention is the result of Elkins for elliptic curve over a number field K. But this number field needs to have a real embedding. And then he showed that elliptic curve, a fixed elliptic curve, has infinitely many supersingular reduction. But unfortunately, our method will not be able to say anything towards the direction about the intersection with Newton's strata, although that is something that we want to do, but not succeed yet. And the second result that I would like to mention is the result of Shaw, who shows that when you have two elliptic curves over a number field, these are still elliptic curves, then there's infinitely many prime V, such that these two elliptic curves are geometrically isogynous to each other over the finite field. So our proof actually builds on the idea of Schacht to use our cleft intersection theory to prove the theorem. So now let me talk about the strategy of the proof. So I guess most people in the room may already guess if I say we want to do our cleft intersection theory on a Schmor variety, then the Schmor variety in this talk will be a Hilbert modular surface. So H will denote the Hilbert modular surface over Z, which has the moduli interpretation to be the moduli stack parameterizing abelian surfaces with OF. OF will denote the ring of integers in the endomorphism of A, and A polarization. Here, A is some fraction ideal of OF. I'm not going to specify. So the thing is, like, since this theorem, the result of this theorem is independent of you push any element in the isogeny class of A. So after pass to a suitable field extension, we can always assume that the OF lies in the endomorphism ring of A. Since this is a GO2 type, you always have a polarization. OK, so, and I use H bar to denote a toroidal compactification. So let me mention is, like, in this case, we'll allow the Green function to have singularities at the boundary divisors, but this is OK. So the ARCA intersection theory we use it actually developed by Bourgass-Guillot, Krem, and Kuh, but like I personally learned it from the reference in a paper by Brunier, Bourgass-Guillot, and Kuhn. So basically, just as since here you have boundary divisor, we allow. So the upshot is that we allow log singularity of Green function at the boundary divisor. OK. So the brief idea is, like, the abelian surface A gives us a horizontal one cycle. When you take the Zariski closure of the point on the generic fiber of H. And then we would like to intersect it with special divisors, which has the geometric meaning is like when you reduction mod P, you have non-simple abelian surfaces. So let me write this down. So the rough idea is the following. So I use curling A to denote the point. So it will be defined over OK after pass through some suitable extension. And we consider Heck orbits of A, which I'll tell you later which Heck operators that I'm looking for. And then we consider intersection of this horizontal one cycle with these are, so there's different names. So classically, these are called Hertzsprung-Witsch-Zagay divisors. Nowadays, for people who work with orthogonal type schema already, they sometimes call it Higner divisors. I'll explain what they are in a minute. So the idea is that we have a lower bound on the total intersection number. So here, let me just say P is a prime which splits in F, and we'll write P equals to frac P prime. So two ideals above P. So the total intersection number will be asymptotically as P goes to infinity around the size P log P. And then the second thing that we show is there's an upper bound for a local intersection number. So I put a V here, it denotes the local intersection number, will be smaller than a little o of P log P. And these two things just imply that there will be infinite, so as P goes to infinity, there will be infinitely many places V, such that the Heck orbits of A over FV bar intersect the special divisor. It's non-empty. And as I said, this special divisor has the property that the reduction is non-simple, and this gives the theorem.
Is there any way to see from this the heuristically correct answer?
No. Oh no. Also,
heuristically.
so yes or no. There's two parts. It's like it depends on how you are going to. So this part is like exact. This part is P log P, and so basically is here you want instead of. So I think the best thing we can show is capital O of P, or oh no. I think the best thing we can show is little o of P, but we don't have any power saving. So if you could have some power saving at this stage, then you would have a positive power for the.
But even just heuristically.
Oh, you mean just a very heuristic?
From this point of view, can you see that square root x?
Give me a second. Good question. I think we should. Okay. So actually, I don't have a very, very good intuition if I think about finite places, but if we think about Archimedean places, I think it's like you need to have really the very sharp Ramanujan for the equal distribution theorem. That's what probably gives you the actual right saving. It's equal to P to the half, and that gives you the right saving. Yes. Okay. Any questions before I run into more details? Okay, so first let me talk about what are the special divisors we're going to pick. Okay, so here's that. Okay, so let me say that for my A is I'll pick an element. So I have a star will denote the Rosati involution. If we use the classical kind of modular space interpretation due to the link papas and the Radcliffe, here is like you have like an ideal class of polarizations, then you just pick a suitable one. Let me not be specific, and that gives a Rosati involution. And then over the generic fiber, so let me write over Q means that I would like to first define it over the generic fiber. And the special endomorphism a special endomorphism means an element inside the actually, let me use B to denote an arbitrary point on the Hilbert modular surface. So inside endomorphism B, such that it is invariant under the Rosati involution, and it commutes with elements inside the OF up to a Galois conjugate. So for any F inside OF, this prime denotes the Galois conjugate of F. So the other way to think about these divisors are those ones that, so for a generic point on the Hilbert modular surface, you have its Picard rank to be true, and for points which lies on the special, which has a special endomorphism, it will have Picard rank at least 3. So, okay, sorry. Give me a second. So now the special divisors will be the subscheme which parameterize points with special endomorphisms. Here C would be so this is a constant. Depend on the type of polarization A. But it will not matter for our argument later. So you can just view it as a parameterized endomorphisms of degree R squared. And to make life easy, I'll assume that the discriminant of F divides R. Because at the end, I would like to consider divisors which are compact. Okay, so the fact is just what I said is, so you have lots of compact divisors. So if I discriminant F times Q, Q is an inert prime in F. And these divisors is non-empty and compact. So the good thing to have compact divisor are two sides. It's like it make life easy for us to do the Archimedean computation. Also, it's like when we do the finite places, we don't need to deal with places with bad reduction because all the points on a compact Schumann curve has potentially good reduction everywhere. Okay, so and when people talk about CUDA program and want to relate the intersection number to Eisenstein series, they need to be a bit more careful about which integral model they are going to choose for the divisor. But for our purpose, it doesn't matter. So we'll just choose the easiest one. So TR will denote the ZRC closure of R inside H bar. OK. So now let me talk about what is the heck operators that we are going to consider. So we always assume that P splits completely in the narrow Hilbert class of F. This is for simplicity because we just don't want to deal with multiple connected components of the Hilbert modular surface, and we only need to work with one type of heck operators to be able to prove our theorem. So we just have this assumption for simplicity. And then in this case is, so the frac P is actually a principal ideal with lambda totally positive. And we consider 1 lambda, this in GO2F. And this gives us the heck operator TP. And then, so the points, TPA, the set of points are one-to-one corresponding to degree P subgroups of the frac P torsion points of A. Sorry. So now let me talk about first how to get the global intersection number. So the idea is like we're not, so the intersection number I put there is more like that you sum up all the contributions from finite places, but if we don't have a second way to compute it, then we're not going to be able to say anything about it. So which means that everything will be in the setting of Arlekov theory is we'll endow TR with a Green function, which I'm going to talk about a bit later. So this will be an Arlekov divisor. And that's why I said previously we would have the Archimedean terms. So we'll consider, instead of consider the intersection number itself, we consider the height of points. So the points later on will be the heck orbit of A with respect to this Arlekov divisor. So it will be sum at Archimedean places. We have values of Green functions, of the Green function. At the support of the generic point, the support of the one cycle at the generic point, and plus our total finite intersection number. Okay. So let me make a remark before I move on to talk about the global intersection number. Is since I already mentioned the word CUDA program, so basically actually it's like if you get a generating series of these special divisors, you can use CUDA program to get that asymptotic bound. But actually you don't need that strong, so you don't really need the modularity result there. So let me just give you an alternative way to look at it using 14th height. So but inevitably, we still need to use Borch's theory. And here's a lemma that I would like to just take the black box. So this works in general for orthogonal type Schmal varieties. So due to Bonnet and Holman. So they say is, so in short, it's like the intersection with special divisors can be related to 14th height. So there exists a meromorphic Hilbert module form psi, which defined over some number field of positive weight, such that the divisor defined by psi is supported on, so this part is on the generic fiber. It's supported on special divisors. This is, I'll write R inside I. I means a finite set. And you can pick R as whatever special forms you want. So for the purpose of this talk, we put R such that all the R's is of form discriminant F times Q. So we want our divisors to be non-empty and compact. So their lemma just says is like whenever you give an infinite set which is good enough, then you can always find a Hilbert module surface whose divisor is supported on these type of special divisors. Okay, I'm going. So in this case, it's like since we have so psi actually gives you a section, a rational section of the Hodge bundle. So this is the universal family of semi-abelian varieties over the theoretical complexification after pass through some suitable level structure. And this is the identity section. So give you of omega tensor k, where omega is this one. Okay, and this is the one which defines 14th height for us, which means a corollary of this lemma here just relates our global intersection number with 14th height. Okay. So corollary is k times hf. This denotes 14th height. Of any point on the special divisor, this means up to adding a constant independent of b is equals to the intersection number. Plus values of Green functions. Or actually, let me be more specific what do I mean by values of Green functions. So these Green functions are actually given by log Peterson norm of psi. Evaluate at, so sigma is an embedding. Evaluate at the point B. So log. And since we work with stacks, although we don't really need to work with stacks in the sense it's like once we pick these special divisors, so the thing is like you want whatever thing you intersect are at least regular. And well, actually, I think in this case it is. So, but even if you want it to be smooth, you can always like choose your integral pass to a level structure which is away from these primes and away from those primes that we're going to discuss finitely many primes. So you can always choose a suitable level structure, then you don't need to worry about the stack issue. Okay, so now we reduce the problem to control 14th height in the isogeny class. So here's a proposition. So assume that A has good reduction at a prime P. So note that throughout the talk, P is split in F. Good reduction means P. It means it's good reduction at every primes over P. Then we have that the sum of 14th height over the Hecke orbit is equals to, so you have P plus 1 elements, so equals to P plus 1, the 14th height of A, plus now comes the main term. So here is the thing which gives you P log P. And this comes from that you just use 14th isogeny formula. So first assume that if A is ordinary, then you know that it's P out of these P plus 1 points, you get a contribution P over, you have a contribution log P over 2 by 14th formula, and the other one gives you a minus a half, so P minus 1. And then we use the fact that this P is split in F, so you don't actually have any isogeny leaves in the Hilbert modular surface. That's why like the map from, then you use the fact that the projection map from the thing with level P structure to the one without level structure is finite flat. And then it tells you that whatever this deficiency number is independent of which abelian varieties that you work with. So you can reduce to the case when you have ordinary reduction. Okay, so now I would like to talk about what happens at finite places. Any questions before I move on to finite places? Okay, so the idea for finite places is actually, so this part is essentially different from the original paper of Shah. It's like we simplify the estimates, just to reduce the idea to all you need is Grothendieck massing theory. Which controls like what is the lattice of special endomorphism looks like when you modulo high and power of P. And then, so yeah, I already mentioned what that is. We want to estimate how many special endomorphisms are there. This is you just use Davenport's lemma to get the estimate. So let me explain this in more details. Yeah, I haven't finished it. Or if you want that part first, I can tell you an idea. Okay, so, okay, thanks. Actually, for letting me talk about finite primes first. So what do we need from Grothendieck massing theory? So I just mentioned it's like after all, we are controlling the number of special endomorphisms with bounded norm. So, okay, so as before, we already assumed that the endomorphism ring of A is just F, nothing more. Okay, so let me use M. So the place is V, and N to denote the Z module of special endomorphism of So let me first write it down and tell you what it is. So B is a point inside the Hecke orbit of A. And so BVN just means that since when we talk about the finite intersection, it will only intersect when A has good reduction. If A doesn't have good reduction, it don't intersect. So I don't distinguish with the generic point and the narrow model of it. So B base change to, well, let me be a little bit more careful. So OKV modulo P to the n. So we do P to the n because we want to use Gaussian-Dick massing series. So when you modulo P, you have PD thickening. When you just modulo pi, you don't. Okay. So, and by Gaussian-Dick massing series, it just tells you essentially, and let me denote L to be the residual characteristic. Okay. So we have when n is very large, this just depends on your point A. And then so the special endomorphism ring, when you go to n plus 1, will lies inside the special endomorphism ring times L. So this just says it's like for something that you can lift. So for something here which you can lift to n plus 1, then you must be a multiple of L. So this is Gaussian-Dick massing theory. Okay, then we can show is, so from Davenport's lemma, this tells us that the number of endomorphisms, so then we know that it is the number of special endomorphisms with, so QS will be just, so S is special endomorphism if degree, so QS is degree S to the half. Less than N is capital O of N to the, it depends on what is the rank of the lattice. So let me say 2m is the rank of MV1. It means, so at this so FV point, the rank is 2m. And so we know that m is at most 2. Okay, so this will be, so you have this many special endomorphisms in MV1, and then we have the discriminant controlled from the Gaussian-Dick massing theory. So you have a discriminant, which is L to the 2mn. Okay, so where am I? So now we need to prove two things. We want to show is that we want to give a bound on like what is the closest point or what is the largest multiplicity it can show up, and what is the proportion of the points in a Hecke orbit which intersect with the special divisors. So let me be more specific. Okay, so we can show for most TP. By most is like when we talk about the density of such primes, it's a density 1 set eventually. And so in our game, we only need to pick infinitely many Hecke orbits to play the asymptotic argument. So as far as we have some property which is good for most of P, we just pick those good Hecke operators to study the property.
Also, that little p log p is not literally for all p.
It should literally for all P, but we did not prove it. Yes. Okay, so give me a second. So we prove that for most of P. Now we would like to do a asymptotic argument. Depends on how large the P is. So let me just focus on those primes P, which is in a range from n½ to n. And then, so first is like we have two parts. First part is that the proportion, so the number of elements in the Hecke orbit of A. And so now I need to pick a neighborhood. So the neighborhood will be 3. No, the 3 doesn't matter. The log n part is the key part. So it just says the number of elements which in the Hecke orbit which intersect with. So we work with a finite set of special divisors which intersect with special divisor is smaller than epsilon p. So it's like for a fixed epsilon for arbitrary epsilon. So later on that epsilon goes to 0. Okay, so this is which means it's like once you choose some cubic neighborhood of the special divisor, it's like mod log n, then you only have at most epsilon p points inside the neighborhood. So it's a very, very weak result similar to the equidistribution result for Hecke orbits. Okay, so the next thing is about how close it can be. It's like for most of the primes, then we have for any points inside the Hecke orbit. So as far as u goes to something which is of size log n. So there's some constants that doesn't matter, but let me write down. So as far as u goes to log n, then they don't intersect. So this point intersects with, does not belong to TR. So which means this gives you the largest multiplicity. So here that so here I did not distinguish like, so the right multiplicity should be, I define it to be the length of some Artinian ring. But in this case, since our thing is actually regular, so it's up to a constant, the same as like modulo p to the n, that your point lies in the special divisor. Since the whole game is like up to a constant is fine, so I just ignore the constant here. Okay, so these two parts, so I haven't explained how to get from here to here, but let me first say actually these two parts just finish the game. So these two parts tells you that the finite contribution at a place V is at most, so there's a bounded constant up to somewhere. And then, so for a small proportion of elements in the Hecke orbit, you have, so log n is similar to log p. And then for all the rest, you have log p. And since epsilon is arbitrary, we can let epsilon goes to 0. So all the constant is independent of, so all here, the p log p are all the constant is independent of epsilon. So that's why this will give you, as epsilon goes to infinity, sorry, epsilon goes to 0, this gives you a OP log p. So to get OP, we need to take into account more like geometric properties of the special endomorphism, so let me not talk about that. Okay, to get these two properties, so if we look at just the expression there, so you see if our n, so if n will be the size of log n, then you just get a little of n. You put say 3. What did I put in there? Okay, so if n is as large as log n, then this will give you a little of n, which means there's only most of the prime p doesn't give you a point which is as close as log n to the special divisor. So, okay, it seems like I rushed a bit. So let me be more precise here. So this is for point 2. If a is, so for point 2, if n is approximately log n, then the number of, so by bad primes, I mean those primes that we want to rule out, which doesn't satisfy property 1 and 2, is smaller than the number of special endomorphisms of A, V, n with norm smaller than some constant times n. Because if B lies on the special divisor, which means B has a special endomorphism, since B lies in the Heck orbit of A, so when you pull back that special endomorphism of B, it gives you a special endomorphism of A with norm approximately n. With norm. So I will use the word norm to mean Q. Okay. So, and this part is by Davenport's lemma this is greater O of n to the m over L to the 2mn. And since my n is log n, then this part gives you so this part will actually be just the O1. Smaller than. I put, will be O1. So which means it's like we just need to rule out finitely many primes at this level. Okay, so. And to get property 1, it's also a count of special endomorphism in the sense is like how many points do you intersect the special divisor? Like the more points you have, the more special endomorphisms you have. So that will be a counting. Let me put it here. Okay. Okay, so in this case, so let me just focus on the primes which lies in the range from n divide log n square to n. So the things that I rule out is just the density 0 set of primes. And then, so the number of bad primes is smaller than, so here, so let me just take m equals to 2. That's the largest possible. So it'll be m squared over L to the 4n. And then so the number of, so each bad prime contributes you, so each bad prime contributes you E times P special endomorphisms. So you divide by E times P, so it'll be 1 over epsilon and log n squared over n. And you just, so since n is of size log n, so this will give you any power of log n you want. So as far as you put as many constants here. So this will be little o of the number of primes. So this just shows you actually our game is much easier than the CUDA program in the sense we don't need to compute the exact number. We only need to control the number of special endomorphisms. And that is just enough from Grothendieck massing theory and Davenport's lemma. So in the last 5 minutes, I would like to talk about the Archimedean places. Since it's already indicated from the finite places, it's like there's 2 things we want to do. So first, we want a distribution result. The second thing is we want to bound the distance of closest point in Hecke orbit to special divisor. And this part, so in the Archimedean case, we are very lucky in the sense we have the equidistribution result of Clausius, O, and UMO. That just tells us like the number of Hecke orbits which can hit a small neighborhood, whatever small neighborhood it is. As far as its area is very small, then it's just a epsilon p number of points. So all we need to do is to bound the distance of closest points. And to do this, we still play the game is like we just want to rule out finitely many primes. So actually, this is a part that we don't know how to just reduce the game to finitely many. So the finite place, if we try hard, we can reduce the game about most of p just to say rule out finitely many. But this is part so far we haven't succeeded in rule out it to finitely many. Okay, so the idea is the following. So let me be a little bit vague. So the distance, so recall is like, okay. So here we also use the fact that TR is compact. So I actually choose a neighborhood which is compact. So I'm in a absolutely safe range to apply the equidistribution result. And in this case, why bounding the distance?
You never have to face going into the cusp where.
Yeah, that's a good question. So when I first talked to you, I thought we need. But for this Hilbert modular surface case, we are lucky we can choose the compact divisor. We don't need to do so. But once we go beyond, once we want to do SOM2 for m greater than 2, we have no choice but treat with cusp.
Then these growth rates of the Green's function in the cusp
Yes.
can blow up quite badly.
So we need to study that. Yeah. Okay. So in this case, we're lucky. So and since the Green function in this case, the Green function in cusp has logarithm singularity, but that is the to the direction they want. So which we actually need to bound is the log of the distance. And this one will be bounded by a capital O of log p. Okay, so for this is we do the following game. If you have 2 points, so I equals to 1, 2. If you have 2 points inside Hecke orbits, which is close to the special divisor, Ri in the set I. And so by applying the Hecke orbit, since we also work with a compact region, so actually all the constants is bounded up to an absolute constant. So it tells you that your point A is actually close. So all the close means something up to log p. So close to the intersection of Tp1R1, Tp2R2. And these intersections are those special points, or in other words, these are a special type of CM points, which isogenies to product of elliptic curves. And these ones, in the classical work of Hertzsprung-Zagay, these corresponding to binary quadratic form over Z, which represents P1R1 and the P2R2. So we would like to use this to rule out the bad primes. So what we do is like, so this just says that A is close to a CM point, and this CM point is unique for all bad prime P in a range. And so which means for all, so the bad prime P are those ones which is representable by a quadratic form, which we have an upper bound for the discriminant. And then just like you use effective Chabatarov density theorem, you'll see that you only rule out density. So because the discriminant of this quadratic form goes to infinity as n goes to infinity. Because the closer the CM point to A, the larger the discriminant will be by a local loss cloud property. That's why we see that actually you only need to rule out a density 1 set of primes. And hence we control both finite and the Archimedean place. We show that there must be infinitely many finite places that you have intersection contribution. And that's it. Thank you very much.